this 5-day long faculty development program sponsored by AICTE. In the first half, we gathered knowledge on practical implementation in collabs. I know all of us are eagerly waiting to hear more from Mr. Shobhoshachi Mukhopadhyay. So, without further delay, I would rather request Mr. Mukhopadhyay to continue his session. Over to you, sir. Thank you. And just a gentle reminder to all the participants that please don't forget to give your attendance at 1 p.m. today. Thank you, sir. Over to you.
Thank you, madam. So we are going to start the next part of our talk. So in the first session, we have learned hybridization, serialization, why we require to do the hybridization, those kind of idea we got, and we have implemented on multi-layer perceptron, and we all got some idea on how can we optimize the code. Okay, and there are several ways. This is not only the single way. So you will see much more tricks and ways of learning the optimization techniques. So basically, let me share the screen with all of you. I request all of you to get ready with your Google Colab, and we will start exploring soon. Let me share the screen. So let me know once the screen becomes visible in front of you.
Yes, sir, this is visible now.
Okay, thank you, madam. So now we will learn the next part, that is all about the asynchronous computation. So is there any comment? Just a second, let me check. Okay, thank you. So basically, you see that if you see the whatever the facilities provided by the today's computer system, because today's computer systems are quite parallel, highly parallel, you must say, and often consisting of the multiple CPU cores and often multiple threads in per core. And obviously there are several multiple processing elements per GPU is there, and when we can utilize the multiple GPU facilities in every device by even interacting with the GPU CPU collaborations. So those facilities are there, and which through which we can take the advantages of the asynchronous computing as well as the parallelization. So basically, like I mentioned in the last session, that unfortunately the Python is not a great way of writing the parallel or asynchronous code, because it requires some sort of the extra help. So you know that Python is, at the end of the day, Python is a single threaded language, and deep learning frameworks, for example, if we talk about the MXNet, or if we talk about the TensorFlow, which has quite easily adapted the asynchronous programming model in order to improve the performances, while PyTorch has its own Python scheduler in order to do the different performances trade-off. So you can see that, the like I was mentioning, that not only the adapting with the asynchronous computing mode, TensorFlow 2.0 has also incorporated the the essence of the imperative programming, because when it started, for example, uh, the Theano, it also started with symbolic programming along with the same thing for the TensorFlow, but later on it adapted with the imperative programming. And like you have seen, that asynchronous computational benefit is given to both of them, Theano and TensorFlow. And obviously, for example, in PyTorch, by default, the GPU operations are asynchronous. PyTorch is designed with the imperative mode, where C++ running in the back end, like I mentioned in earlier session. So when you call a function, it uses the GPU, and the operations are enqueued with the particular devices, but not necessarily executed later. So basically, programming structures goes there, instruction goes there, and that remain in queue. One by one, it has been executed. So basically, we will see that how we can execute the asynchronous computing with the hands-on session. We'll be able to see that what are the benefits of the asynchronous computing. So before running with the code, few things I want to highlight, a few notes on the code for all of you. For example, here you can see one module is given there. an OS module when we will run the code. So basically, what is the benefit of the OS module? Because you see in the code section, if you can see, we are importing OS. What is the benefit of OS? So basically, OS module in perform in Python, it interacts with your operating system. Okay. So basically, OS comes under the Python standard library utility modules, and this module provide a very much portability in terms of the operating system dependent functionalities. So OS and OS.path include many functions to interact with the file system. So anything related to operating system, any functionality related to operating system, importing OS module in Python or Python related platforms is quite handy. And obviously the sub process module, you see we are also importing sub process. So basically sub process module which will provide you the function named call. Okay, so this function allows you to call another program and wait for the comment to complete and return the code. So this sub program importing uh, will give you the facility to calling another program, wait for the command to complete, and then obviously return the code. So this type of functionalities and facilities we are going to get. So let's start with the coding. I hope that all of you are ready with your I mean Google Colab, and please click on the pop-up. There are two pop-ups already fast up. Those who are new to Google Colab, you have seen that. Please click on the plus code button, and I would say please open a new notebook. Okay, you can go to file section. Okay, and if you click on the file section, you can see there is a new notebook option is there. Open the new one. Okay, and give a name of the notebook asynchronous computation. Okay, and obviously there will be .py .ipy in the extension for the interactive Python notebook extension is there. Click on that, rename it asynchronous computation. Give the notebook name, open the new notebook, and give the notebook name asynchronous computation, and then gradually start to explore the beauty of the asynchronous computation, like we have seen in case of the hybridization and serialization. Now we'll see the asynchronous computation. Okay, so just go through the code. I'm just scrolling it up. So like you have done, please install MXNet, then do the install D2L and import them both. Then obviously import OS for interacting with the operating system, subprocess for calling the another program, compile it and wait for the compilation, and then obviously importing the NumPy. Okay, then from the MXNet you incorporate AutoGrad, Gluon, NP, NPX. Okay, those operations so one by one you incorporate, and then finally npx.setup you run it, and you will get the following type of outcomes. Okay, so at the end it will show the installing the collected packages D2L and successfully installed D2L 0.616.5. Okay, this type of outcome you will get. Okay, so first do the basic steps, then we will see the asynchrony in backend. Okay, just incorporate it. Also, just a second, let me give you that in chat box also. Just a second. What is the overview? Yes, sir. Acha. Done. So let me know once you are done. Okay, just let me know once you complete the step. It is 11:56, so I request all of you to complete it by 11:58. We will then go to the next part. Okay. Kindly complete it by 11:58. I have already pasted that in your chat box. It should not take much time. So kindly incorporated within 1158. Okay, thank you. Thank you, Abhishek sir, for completing it. Thank you, Anubhav sir. So let's wait for 1 more minute, then we shall go ahead. Okay, Somodip sir. Thank you, Orpita ma'am. Thank you. Thank you for the update. So gradually, all of you have incorporated it. So we are there. It's 11:58. So I am moving to the next part. I believe that all of you have done it. Thank you. So let's move it to next part. Okay. Thank you. So now you will see the asynchrony via backend. So for a warm up, we can deal with a toy problem where we want to generate a random matrix and multiply it. Okay. So let us do it in both in NumPy and mxnet.np to see the difference. Okay. So you see that first of all we have incorporated in NumPy while generating the random matrix. Okay. And you see once we incorporate it, it is taking time after doing the NumPy dot. It is taking time 1.2901 second after running the code. And if we are incorporating with the mxnet.np, you can see the the output is coming up. Okay, after generating the random matrix, it is taking time 0.0092 second. So clearly, mxnet is giving you the better result, much more faster result. Okay, so let me paste the code in your comment box. Okay, kindly run it and see the beauty of the mxnet. Okay. So it is sent to your chat box. So kindly have a look. So basically, we have seen that after executing it, that mxnet is giving you the better result. It is quite faster result in comparison to your numpy. Okay, so since both are executed on the same processor, now the question is that both of them we have incorporated over the same processor. Okay, so something else must be going on, which is forcing the mxnet to finish all this back-end computation prior to your numpy. So what is that X factor? Okay, computer execution while front-end is controlling the Python. Okay, that means it is there is something going on in backend which is helping the mxnet to incorporate it faster. Okay, because processor is also same. In front end we are using Pythonic Flutter. So it is the backend which is giving you the faster execution. Okay, so that means the computation is fully executed by the backend while the while the front end returns control back to the Python. So that's the overall scenario. Okay, let me see the comment box. So it is a 12.1 by 12.2. Please finish it. Asynchrony via backend section code. Kindly finish it by 12.2. Already Abhishek sir has done it. Thank you very much. So you have seen that backend is playing the role of the executing the computation and returning back the result to the front end. Okay, and there is something going on in backend that in spite of using the same processor, same Pythonic platform, we are getting the better result. I mean, much faster result in MXNet in comparison to NumPy. Okay. So once you are done, just let me know. Let me know. Uh, we will wait for a few more seconds and move to the next part. Thank you all those who are commenting, all my respected participants. Thanks to very much for your precious feedback and all the precious acknowledgement. Otherwise, this session would have been incomplete without your corporations, prior corporations and friendly corporations. Thank you. Thank you. Thank you. So we are moving to next part now. So now we will see that, for example, whenever we are using now with the benchmark, okay, D2L benchmark, okay, we're executing it and incorporating npx weight all. So now we will see what type of outcome we will get, okay, because you see the front end language, the front end coding, mxnet is running in the front end interaction purpose, that is Pythonic. But you see in the back end is something there which is giving it the optimum result. And here you see, like I mentioned in the first session, that in back end C++ is playing a very, very important role in terms of the faster execution of the it. Okay. So that's the reason you see that you are getting this type of the optimum outcome. Okay, now you incorporate it. I am just pasting the code in your comment box. Okay, and see the benefit of the npx dot wait all. In general, like I was mentioning, that operations can be issued in the front end. Okay, but it is then passed to the back end for the execution purpose. Okay, so it is the back end which actually manages its own thread. Okay, by continuously collecting and executing the all the queued stacks, because as I was mentioning that whenever you the front end is passing the instruction to the back end, so all the instructions are in queued, it is one by one, it is executed. So like here in front end you can see the mxnet module with Pythonic platform, and the backend is C++ there. C++ is gradually executing one by one steps. Okay, so there is a computational graph. It deals, backend deals with a computational graph. Okay, so whatever the instruction you are sending, computational graph is there. It is following the optimum path. Okay, so some sort of the it has to create some independency in order to execute that, because depending on each other will not be able to give you the benefit of the parallelism or parallel computing. So that's the reason, like we have seen in the first session also, that we have to become the platform independent, front end platform independent. Okay, front end there will be some user friendly code which people are quite accustomed with. For example, in imperative in nature, people will write some code, and in the back end, with the help of the computational graph, okay, it will execute the code much more robust and faster. Okay, so the back end works on the basis of the computational graph. Okay, whatever the instruction you give via front end, back end works with the computational graph, and it gives you optimum outcome, like we have seen in earlier few examples. Okay. So let I will wait for a couple of seconds more, and then we'll start the next part. So already Ankur sir, Amit, Abhishek sir, everybody has, Amit Majumdar sir, Abhishek sir, everybody has sent their confirmation that they have executed that part of the code. So now what we will do, we will start the next portion. Okay, we'll see another very trivial example in terms of to understand the dependency graph a much better way. Okay, so you see there are two numpys arrays we have defined, and then we have what we have done. We have done a very simply arithmetical problem execution has been done there, and you see we have got the array. Okay, uh, now uh, you can also incorporate it in your R console as well. Sorry, in your uh, Google Colab as well. I am just sending you. Okay, so whether it is an easy problem or complicated problem, it is being tackled with the backend computational graph. Okay, it is the backend who is dealing with all those computational graphs. Front end is sending the instruction to backend. Instruction are going in queue. Okay, and the backend is executing the queue with the help of the computational graph. Okay, and then it is sent back the result to the front end. Okay, and according to that, the things are going on. So always remember that in spite of you are using the same processor, in spite of you are using some same type of the front end platform, still due to some backend uh, efficacy of backend, you may get some sort of better result, better outcome, better runtime, like we have observed in case of the MX, the difference between to justify the difference between the executional power of MXNet and NumPy. Okay, so whenever the front end thread executes the first of the three statements, whatever written there in the above code, it simply returns structs to the QE of the backend, and the last statement return to be printed. So what does it happen? That front end will wait for C++ backend in order to in the backend thread in order to finish all those results and sending back the variable result of with Z. Okay, and one of the benefit is actually that Python is a front end thread, but it is not doing the actual computation, which I said few minutes back, that it is not the front end language is not doing the actual computation. Rather, it is passing the instruction, and the backend with the queue of the instruction and the help of the computational graph, it is generating the result. Okay, so that means there is a very little impact on the overall programming performance Python has. It is only as a user friendly medium to take the instruction from the developer or the coder. It is taking it and it is sending the instruction back to the backend, and backend with the help of the QE, it is doing execution everything with the help of the computational graph. That means Python has nothing to do with overall coding scenario. Okay, it is the backend which is doing that, and that's the reason with the help of the C++, PyTorch is so much elegant and so much faster in terms of the execution. Okay, so let me see the comments. I think already all of you have already incorporated it. Okay, done. Thank you all. So we will move to the next part, that is the barriers and blockers. Okay, that we will see one by one. Okay, now you see there are a number of operations which force Python to wait for the completion. Okay, because Python has to wait before the backend execution is done. So what are the cases? Most obviously, whenever we are writing, like for example, npx.waitAll function, it wait until all the computation has completed. You can see that the extension is given npx.waitAll. By the name, you can easily understand that it will wait until all the computational tasks is being executed. Okay, so regardless of the when whatever the instructions goes on there, it will wait until the computational task is being incorporated fully. Okay, so in practice it is a bad idea to use this type of the operator unless absolute necessary. Okay, because this may lead to poor performance, because if you wait for all, then you are not being able to utilizing the full timestamp. So we can play some trick there also. So can we make some tricky approach there that we'll see in upcoming scenarios and upcoming examples. And along with that also, that if we just want to wait, a specific variable is available. We can call jet.wait to read. Okay, Okay, in this case, mxnet blocks return to Python. Okay, until the variable z has been computed. Okay, other computation may continue afterwards. So see both the cases. Okay, first case, what will you do? We will explore the barriers. Okay, which are basically making the Python dependent in terms of the completion aspects of the backend task. So first of all, we will explore the example with wait all. Okay, and the second example we will explore with the benchmark. Okay, and then after we will run it, and we will see this type of outcomes will appear. So we will be able to see that both of them are almost same timing. Okay, so these are obviously blocking the operations whatever we are basically recommending. Okay, so how can we tackle that? How can we tackle with those blockers which are actually uh, blocking the Python from having the optimum performances? Okay, because NumPy does not have any type of the asynchrony, so we have to go by asynchrony. Some sort of asynchrony is required. Otherwise, wait dot all or wait to read, this will make the system wait much more longer than the desired cases. Okay, so this is another scope of optimizing your code. Okay, so first of all, let's explore the barriers. Okay, then we will find the fine tuning path by which we can overcome that particular barriers. Okay, and how we can block those barriers. So I have shared the code in your comment box. So kindly run it. Okay, and you will be able to see that wait all and wait to read in both the cases are it is taking almost nearby same timing. Okay, thank you already. Somodev sir has already incorporated it. Okay, it's 12:15, so I am waiting up to 12:16 to all of you to run it. Then we will go to the next part. Okay, so we can see that wait all and wait to read both are taking the same type of timing, almost same type of timing, nearby timing to execute this portion of the code. So these are the basically the barriers. Python has to wait that much of time to complete the task from the backend. But can we do some asynchronous trick that we don't have to wait for executing of the all these steps, and we can utilize much more faster computation. Okay, those things we will explore now. Okay, thank you those who have done it. Very nice. Thanks for the great efforts from your end. Okay, so we will wait for a few more seconds and then we will start the next part, execution of the next part. Okay, so let's move to the next part. Now here say, for example, we are doing both of the operations. Like for example, one we are doing with the numpy conversion. Another one we are doing with the scalar conversion. And now you see what type of benefit we can get, because you see that copying small amount of the data frequently from mxnet to numpy and back can destroy the overall efficacy of the code. Okay, so since each such operation requires the computational graph to evaluate all the intermediate result to get the relevant term before anything else can be done. Okay, so that's the reason it is better that that to do some sort of the asynchrony. Okay, and the next improving the computation will be done in the next step. So now you will see couple of examples with the type of the whenever we are doing the numpy conversions and whether we are doing the scalar conversions. In both the cases, we will measure the timing. Okay, in that case, we can see numpy conversion is giving you the better, faster result, executional result in terms of the scalar conversion. Okay, here you can see. So basically, we will see that using the as dot as numpy is making the system work much more faster. Okay, because you see that as dot numpy, okay, it has the faster conversion rate in comparison to the scalar. For example, dot item function. Here we are using dot item function. That explanation has been added there. If you see this portion, the explanation is given there, that in the last conversions, if you see, to numpy via z add dot as numpy function. Here in the example we have used b dot as numpy function. Okay, and conversion to scalars via dot item function, okay, are blocking. Okay, since numpy has no notion of the asynchrony, so it needs the access to the values, like for example the in order to print function. So but it is quite faster than the scalar conversion. That is also true. Okay, now these are the scenarios we have seen, that what are the barrier scenarios, what are the blocking scenarios, and how we can do the numpy conversion, how we can do the scalar conversion. Okay, with the help of respectively as dot as numpy as well as dot item functions are there to respectively to complete those tasks. Then we will see the improving the computation. Okay, so we have gone through the blocking and barrier part. Now we will explore the improving computation, and before that I am just copying and pasting it in your comment box so that you can explore it in your uh, collab. It's now 12:20. We shall wait for another more minute, and then we shall go to the next part, improving computations. So already our respected participants are saying that they have already done that part. Thank you very much. We will wait for a couple of seconds and then we shall start. It's now 12:21 already, so let we can start it rather than waiting much. So basically, whenever we are looking after the, for example, improving the computation, okay, so it can be heavily multi-threaded system. So if it is a heavily multi-threaded system, for instance, even if we have the regular laptops, if we look after the regular laptops, it has the 4 threads. Or for example, if you go by the multi-socket server, that this number can exceed to 256. So the main funda is that we have to take care of the overhead of the scheduling operations, because that sometimes become very significant, and that is why you have to be very very careful to get the desirable outcome in terms of the computation. That scheduling can the scheduling take place in an asynchronous manner? Okay, first of all, can the scheduling take place in an asynchronous manner, and can we follow the parallelism? Okay, so these two things if we can explore, okay, then we can get the benefit of this type of the computations. Okay, now for example, let us see the following case. Okay, that we can simulate the synchronous execution by inserting a way to read barrier in between each edition. Okay, whenever we are incrementing a variable by one multiple lines, one is this in sequence or asynchronously, we will see both the cases. Okay, after doing all those installation part, we will do one example for the synchronous case, we'll do one case for the asynchronous case for doing the addition, incorporating the addition operation. Okay, we will basically define one numpy array with ones, series of ones. Okay, and then we will incorporate the summation step y equals to x plus 1 for both the cases. And one case we will see, whenever we will doing the synchronous operation, the comment will be y dot wait to read at the end. And if we are doing in asynchronous way, it will be npx dot wait all. That is the differences uh, while executing the synchronous and asynchronous operations. Okay, in case of synchronous operation, we have to define the n-dimensional array, obviously, and we will execute the results. Okay, and this type of following type of outcome we will get. Okay, first of all, it will show the all the installation part, and then at the end, okay, you will be able to see these two result. With the synchronous case, you are getting 2.01404 second, and asynchronous case you are getting 0.7279. So you can see the significant improvement we are getting by following the asynchrony. Okay, and obviously do not forget that whenever you are incorporating the synchronous and asynchronous operations both in parallel to test the efficacy of the code, that in case of the synchronous operation, you will use dot wait to read function like you have done earlier, which is the barrier basically we have seen. And in asynchronous mode code, we are using npx dot wait all function. Okay, so these two things you have to be very very careful. Okay, once you run the code, check the beauty of the efficacy of the asynchrony. Okay, so please execute it and let me know once you are done. So it is already 12:25. So by 12:27, kindly complete it. Then we will go to the next part. So basically, just a second. Let me copy and paste it in your comment box. So I have sent it in your comment box. Kindly incorporate it and let me know once you are done. Thank you. Thank you, Shomodeep sir. So it is between synchronous and asynchronous performance. Okay. Thank you, Amit sir. So you will wait for 1 more minutes and then we will start the next part. Okay. So basically, let me because this we are at the end of this notebook where we have learned the beauty of the asynchronous computing. So basically, I will explain that after once you complete your coding part, and then we'll go to the next notebook. Okay, where we will learn the another tricks of the parallelism. So let us wait for a few more seconds and then we will wrap it up. So basically, by incorporating it, we have seen that deep learning frameworks, whatever we have incorporated here, it may decouple the Python front end from the executional backend. Okay, because at the end of the day, backend is playing the trick. Even if you are using the same processor, same type of the platforms, front end platforms, but you can see that due to the backend efficacy, you can optimize your result. Okay, so that type of efficacy you can achieve with by the first asynchronous insertion comment into backend and associated parallelism. Okay, like one example I have given there. Okay, if you are breaking up the program in a three stage, T1, T2, and three stage, and if you are doing the 10,000 computation, so the synchronous computing, if you are doing it in synchronous way, it will be like 10,000 into T1, T2, T3 within bracket. But if you are doing the asynchronous computing, so it will not follow up each and every step. Rather, it will pick up any particular step to follow up. Because once you are going each step follow up with the backend, it will slow up your speed. So rather, you have to do it in a tricky way, such that you can save your time. Okay, so asynchrony, what can the benefit you can get? The asynchrony leads to a rather responsive front end. It makes the front end responsive, and however, you use caution not to overfill the task. Obviously, you have to one thing, you have to be very careful that you should not overburden or overhead with the QE of the task instruction. That thing you have to be very careful. Okay, and obviously nowadays due to the hardware development, we can see that a lot of chip vendors are offering a lot of some sort of the chip, a lot of sophisticated performance analysis in order to get the fine grained insight, in order to facilitate the efficacy of the deep learning. And obviously we have to be very careful about the mxnet memory management to Python, which will force the backend to wait until the specific variable get ready. So functions, for example, such as print, comma, as numpy item, will have this type of the effects. So we have to be very careful while doing the asynchrony, because careless use of synchronization can ruin the performances. So we are looking for the optimization, and each and every second is very important here. So we are done with the asynchronous computational part. So we will go to the next part. Okay, so I think we is there any doubt with this particular part, or I will go to the move to the next notebook. I believe this part is done by all and everybody has incorporated it. Is there any doubt from this part, or I shall move to next part, next notebook? So I will wait for your response for 1 more minute. This is 10:30. If by 10:31, if it is if any question arises, please ask within 1 minute. Otherwise, we will move to next notebook part. Okay, you can move, sir. Thank you, Abhishek sir, for your kind feedback. Thank you. So I am stopping the screen, sir, for a moment. Hello. Now we will learn in this section about the auto-parallelism computational performances. Okay, we have learned the hybridization, we have learned the serialization, we have also understand the importances of the asynchronization. Now we will cover up the auto-parallelism part. So basically, let me share the screen with all of you. So once the screen appears in front of you, just let me know. So what you do here, doing the auto-parallelism of the computational performances, you go to runtime. Okay, you click on runtime. Here you will see change runtime type. Here you do hardware accelerator. Click on the hardware accelerator and select GPU. Okay, and save it. I am repeating the step. Go to runtime. Okay, then you do the change runtime type. Okay, you will see none there. Here I already have set up GPU. There are three options: non GPU, TPU. You can select GPU and save it. Okay, and then you just write down these two lines. I am sharing in your comment box as well. Okay, so then you will be able to incorporate it. So pip install d2l equals to 0.1.16.5 and pip install mxnet c101. Okay, these two things kindly incorporate, and then you will be able to see once you are running a GPU, this all requirements will be fulfilled as per the module package requirement. And then once we are done with it, you will be able to see this type of the following output regarding the downloadation of the packages. Okay, we'll be able to see successful install packages mxnet, successful install mxnet. Okay, then we will go for the automatic parallelism steps. Just write these two lines first. Set your runtime at GPU and then please incorporate it. Let me know once you are done. So this is now 12:35. So I would request all of you to complete it by 12:36 because this is simply two line of code. Once you are done, please let me know. I will move ahead. But do it in a new notebook. By the way, once you are doing it, please do it in a new notebook. Huh? Open, go to the file section, open new notebook, and give the name Auto Parallelism Computational Performances. Okay, give the name as auto parallelism computational performances, and already I guess you have changed your runtime. Go to runtime and change runtime type into GPU. So are you done with that? Kindly let me know in your comment box. So it's already 12:38. I hope all of you are doing it or already completed it. Can you please anyone write in the comment box that is it okay? Should I go ahead? Am I audible? Okay, yes, you are audible. Yeah, it's done. You may go
Yes,
ahead.
sir,
Okay.
you are audible.
Okay, thank you, thank you. Actually, there was no response coming up, so I thought, is there any audio problem or not? Okay,
We
thank
can
you.
hear you clearly.
Okay, thank you, madam. So in this notebook, hope the renaming is done as the auto parallelism computational performances. Earlier we have done about the asynchrony. So now we will see, once you are done with the step, that automatic parallelism. So in case of the automatic parallelism, you see, like I was mentioning, the deep learning frameworks, for instance, PyTorch, MXNet, automatically construct the computational graph at backend. Because last section we have seen that the backend is playing a very, very important or significant role. Okay, and you see, for instance, whenever front end is sending the instruction to backend, it can actually execute it, okay, with the help of the computational graph. So using the computational graph, it actually, you will come to see what are the dependency factors. The more you will go with the non-interdependent, the more you will improve the speed with the parallel help of the parallelism. Okay, now typically a single operator, for instance, other the computational resources you can utilize with the uh, multiple, you can utilize with the resources on the all CPUs, or go by a GPU or the collection of the GPU. So basically dot operator will use by the all the cores or threads of the CPUs or GPUs. Okay, so basically we'll see that how can we incorporate one by one. Okay, in generally, if your system is supported by one GPU, then it will collaborate with the existing CPU. And if there is more than one GPU, then it's fine. At least two GPU will help us in executing the next experiment section. Okay, and if not, if you have only one GPU, then it will collaborate with your existing CPU. Okay, so first step, you just incorporate this particular line from mxnet in import np comma npx, and then d2l from mxnet as d2l npx dot setup np. Just write this line, and then what will you do? We will see the device factor. Okay, how can we do the parallel computation on GPUs? That thing we will explore. This is going to be quite exciting to see these facilities. Can you see the screen? স্ক্রিন শেয়ারিংটা বন্ধ হয়ে গেল নাকি?
Yes, sir. We cannot see your screen right now.
ওকে ওকে ওকে, আমি তাহলে মনে হচ্ছে কোনো কারণে স্ক্রিন শেয়ারিংটা স্টপ হয়ে গেছে।
Yes, sir.
এক সেকেন্ড, জাস্ট এ সেকেন্ড। Is it visible to all of you?
This is coming. This is taking a lot of. Yeah, it is okay now. We can see it.
Okay, okay. Thank you,
Thank
madam.
you.
So, like the thing I was mentioning, that this is the automatic parallelism part. Okay, that backend is doing the task with the help of the computational graph. Okay, which by following the instruction from the front end, and we will execute this section with the help of the GPUs. Okay, if your system has one GPU, then it will collaborate with CPU and incorporate it, or if it has more than one GPU, then two GPUs is sufficient to execute the next task. So first of all, please incorporate this part. Okay, then we will go to the next part of the parallel computation on GPUs. Okay, then we will see how the GPU is helping in terms of the parallel computation. This is a very important part, because already we all have seen the hybridization asynchronous computation. Now this parallelism will give you the idea that how GPU executes the parallelism task while doing the executing the deep learning based computation, because this will give you idea that whenever you are planning of something with a lightweight processor devices, like for example, you are doing heavy load work in your cloud, you want to incorporate a lightweight module in your edge devices like smartphone. So what will be the what are the tricks of avoiding the computational complexity? That is going to play a very important role. You have to reduce the time complexity, but how can you do that? So those type of tricks and techniques you will gradually enlighten with this type of by following this type of lectures and hands-on sessions. Once you are done, let me know. Please write in comment box if you are done with this particular first part before parallel computation on GPUs. Please write in comment box that part. Then I will start explaining the next part, parallel computation on GPUs. We will see that through this experiment how can we get the optimized benefit from the code. Are all of you feeling tired by typing the codes, or they going through the hands-on session continuously? This is if you want, I can stop here, but this is the last notebook I want to share, because this is very interesting, because otherwise the session will remain incomplete without parallelism, explaining the parallelism with GPU, with the help of GPU. That is a very important thing. So at least consider this as at least last notebook. You can I would request all of you to incorporate it, because all of you have done asynchrony part and hybridization part quite smartly and very nicely. If you can incorporate it, you will get some idea that how GPU is tackling the parallel computations. And in case of if you are going for the product development purpose, with the help of edge computing, it can remain benefited purpose as there as well. So I would request all of you to kindly just complete this notebook as well.
Yes, sir. There are comments in the chat box. No, sir. It is a good session going on. Please continue. And
I
great
can't see the
session.
chat box. I mean, is there any comments are coming in chat box? It is not appearing in front of me,
Yes, it is.
unfortunately.
All right, but we can see the comments in the chat box right now.
Okay, just a second. Let me check. Okay, okay. Now it is appearing in front of me. Okay,
Okay.
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 Somehow I was not able to see it. Okay,
All right.
okay, 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 okay.
All right.
Actually, the comments were not appearing in front of me. That's the reason I was thinking that what happened suddenly.
All right.
Okay,
But
okay.
now we
So
cannot see your screen. There are more comments. Purposeful session. Great session.
yeah,
Please
yeah.
continue, sir. Okay.
Okay, okay. Thank you, thank you, thank you, thank you for your precious feedback. So we will now go on the that part, the doing the parallel computation on GPU. Okay. So basically, uh, what we are doing now, we are defining the devices. Okay. So we are basically allocating two variables, x underscore GPU1. Oh, screen is not visible. Just a second. I think again it went to. Let me share the screen. Something, some problem is going on. Okay. Now can you see the screen? I think it is visible
Yes,
now.
sir. Now
Okay.
we are able to see that you have started sharing. Yeah, now it's okay. Fine.
Okay. So parallel computation on GPU section, you see, we are defining two variables. As I have told you that now we require at least two GPUs. So if your system has one GPU, then what will happen? That the first GPU one will execute for the GPU part, and GPU two will redirect to CPU. Okay, and if you have more than one GPU, then it's fine. Then it will by default consider these two, at least two GPUs to execute this operation, this experiment. So first case, what will you do? We will write this part device d12 try all GPUs function, and then you will define the run x. Okay, and then return x dot x for in range 50. We are taking the considering the range 50, and then you print it. So it will give you all the NP random uniform of size 4000 by 4000 with x underscore GPU1 and x underscore GPU2. Okay, just do this part. Then what we'll do, we will warm up both the GPUs. Okay, with with setting the time for them. So first execute this portion. Huh? Once you are done, just write in comment box. It is now 12:50. So please complete it by 12:52.
Hello, sir.
Yes.
It will be helpful for us if you paste the code.
Okay, 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 okay. Just a second. I am pasting it in the comment box section. Oh, sorry. Just a second. I have sent you in the comment box section. Huh? Kindly incorporate it. Oh, it again. Can you see it now? In the comment box, I have shared all the codes.
Yes, sir. It's visible.
Okay, so auto parallelism. Then you run after you first you pip install D2L MXNet. Then you go to automatic parallelism with the help of the by incorporating the MXNet, importing NP and NPX. Okay, and then finally you just define the XGPU1 and XGPU2 with the device. Okay, device equals to D2L dot try all GPUs, and then you define the XGPU1 and XGPU2. Okay, so if you have more than one GPU, then it's fine, it will automatically take it. And if there is no two GPUs, only one GPU is existing, then what will happen? GPU, for example, XGPU1 will go with GPU, and XGPU2 will consider your system CPU for incorporating the code. So are you done with it? Then you type run XGPU1, XGPU2. That will help you to execute the GPU1 time and GPU2 time. Just a second. Let me give it in the comment box. Oh, I think it is not. Is the screen sharing stopped? Oh, some problem. Glitches going on. Just a second. Now I think it would appear. It should appear. So you run it. Okay. So it will give you the GPU1 time and GPU2 time. Okay. So you can see all the running time in both the GPU cases. Okay, run x underscore GPU1 GPU2, then you write npx dot wait all. Well, for all the execution are done, then you do for calculate the time for GPU1 and GPU2. Okay, so if you now you can see that if our last cases in the during doing the your executing the asynchrony part, we have seen that wait all is playing a barrier. Okay, so what if we remove the wait all statement between both the tasks? Then the system will become much more free to parallelize the computation for both the GPU automatically. So that is a very important significant step. That can we remove the wait all statement, because in the last, if you remember, just few minutes back, we have executed that in asynchronous computational part, that wait all is making the system slower. Okay, so can we remove this wait all statement part, and we can incorporate the same coding on them? So how the GPUs, both the GPUs are going to perform? Okay, so those things we will see in the next part. So once you are done, just let me know. Okay, it is now 12:57. We will wait. I will wait for 12:58, and I will go to the next part. Okay. I hope gradually all of you are able to see now GPU1 time and GPU2 time. Okay, what are the run times? You can now clearly see in your Google Colab. So are you done with it? Kindly write in your comment box. So I will show you the example without wait all statement. Okay, that how can you do it without wait all statement? So we have seen that wait all statement is affecting overall scenario. Now whenever we are doing the without wait all, so it will help us to do the parallelization now. Now in the comment box section, rather we are doing it in separately. Okay, you can see in the running the code section now with d12.benchmark we are clubbing them together, GPU1 and GPU2, and we are running xGPU1 run xGPU2 and npx wait all. Okay, rather than putting it separately, we are clubbing them together and running it. Now you see here, if you add this to runtime 105 second and 103 second, okay, it will give you 208 second in overall. Okay, and now if you are doing it in a separate mode, okay, now you just calculate the runtime. Okay, so in both the cases you can see the runtimes are almost coming closer to each other. In both the cases you can see the runtime is almost coming closer to each other. So let me share this portion of the code with all of you such that you can run it in your let me give it in comment box section. Okay, so GPU1 and GPU2, once you are running them together, then what is the amount of the timing you are getting? Okay, you have already seen GPU1 and GPU2 time. Now if you are running them together with wait all, then what type of the timing you are observing now? That we will explore. So let me share it in the screen, sorry, in the comment box. Okay, so now I have shared it in the comment box. So please run that thing in the code section. Okay, and now observe the timing. Okay, that what is the timing now you are getting by running GPU1 and GPU2 together. Let me know once you are done.
Hello, sir.
Yes.
Actually, in previous running, so it is
Uh-huh.
still now it is going on, and it is
Okay.
taking time, GPU1 and GPU2, because GPU1 has completed, but still we are waiting for the time taken by
Okay, okay, no,
GPU2.
no problem, no problem. So that thing that is not a problem. Just I am telling you, it will get nearby time. Okay, adding them together, okay, should give you little bit lesser time than the previous one. Okay, doing it separately, but almost nearby timing will come up. It actually lot of people are at the same time using Google Colab, so it may happen that system internal system is becoming quite slower, and it is the daytime, so nowadays a lot of software companies are also exploring Google Colab, so that's maybe the reason it is slow, it is going a little bit slow. But what you can do centrally, because I will share this code with all of you, you just understand the code, you can run it later on and you can check out the outcome. Okay, if you are running it after almost after in the evening time, late evening time, after 9 p.m. and something, it will give you a very fast result. Now it will take, this is now office hour, it will take some little, it will go some slow, little bit slow.
Sir, how many,
Okay.
sir, just a minute, how many GPUs we can, we are provided in Colab? Is there any limitation? Or
Look, in generally Google Colab you will get the support of Nvidia Tesla one GPU support is there. Okay, So if you are executing it for GPU1 and GPU2, GPU1 is going for that NVIDIA Tesla, and GPU2 is taking the support of your system CPU. Okay, this is how it is incorporating here. But if you go for any high performance machine, there will be multiple number of GPUs. So there is this type of two getting support of two GPU operations are quite easy. Okay, so there is nothing that will take much more lesser time than the time you are experiencing here. Okay, and you will see that whenever you are incorporating both of the GPU operations together, it will take much lesser time than the earlier case. Okay, for example, in my case, GPU1 is taking 105 second, GPU2 is taking 103 second when I am doing it separately. So if I add them up, so it will approximately take 208 second. But if I running them together, okay, GPU1 and GPU2, the last code which I sent to you, it is taken, it is taking 170 second. Okay, I think you can see my screen, so you will be able to see that.
No, sir,
Oh,
it is not visible.
problem, some problem is going. Anyway, can you see it now? ঠিক আছে?
Yes,
Can you
yes,
see it now? Okay. So
yes.
you see in from my screen that whenever we are running GPU1 and GPU2 together, it is giving you 170.5391 second. Now this is much lesser than the time it is taking GPU1 and GPU2. Sometimes it may go closer also. It depends on the system performances, but it is expected that it will take, whenever running them all together, GPU1 and GPU2, it will take lesser time in comparison to that, because the more you will remove the dependency on wait all statement, because earlier we have used npx.wait all twice. Okay, so it is putting the barrier somehow. You are killing your time almost. You can see, if I go by this particular example, we are going to lose 38 second, 38 to 39 second. Okay, but if we go by this approach, if we club them together and only use npx.wait all only once, then what is happening, these both statements are going in parallel way, and we are able to save much more time than earlier. Okay, so this is how we can proceed. Okay, so I hope that this part is incorporated by all of you. Now you will see the parallel computation and communication. So in many cases, we need to move data between different devices. Okay, we may have to move from the CPU and GPU, or between different GPUs. But for instance, we want to perform the distributed optimization. Now, if we are going, earlier we have seen the optimization. Now, if we are planning to go by the distributed optimization, so basically we need to aggregate the gradients over multiple accelerator cards. Okay, we can utilize that. So let us simulate this by computing GPU and copying it, the result back to CPU. Okay, so if you incorporate that code, for example, what we are doing, we are implementing in GPU and we are copying it back to CPU. So what is going to happen now? So basically, copy to CPU x return y copy to npx.cpu function. Now this CPU function, you see, it will consider all the CPU related stuff. Okay, and if you are running them, for example, with d12.benchmark run on GPU1 and d12.benchmark copy to CPU. Okay, and then you see both the cases. So in case of the GPU1, you can see that it is giving you 122 second, 122.7829 second, and copy to CPU is giving you 3.0715 second. Okay, so this type of the operations you can perform, where you are executing certain portion on GPU and you are making copy to CPU. Okay, that is also can be done. But the thing is that it is always whenever this type of operations you are doing, basically, that you need to compute the gradient of the mini batch. So mini batch means you are splitting the training into some segments, training operations. So this is the mini batch operation. And what is happen when you go by the backward propagation? Our target is to reduce the error margin. Okay, so this is the stochastic gradient process in general we follow. So during that, there is one of the way which we can utilize the bandwidth while making GPU running. that is the one of the bus bandwidth, that is PCI Express. We call it PCI Express. We can take the help of that also. So I will show that before you run it, then I will show it. The PCI stands for the peripheral component interconnect. Okay. So that PCI interconnect, with the help of that, we can take the optimization operations in between the performance, trading of the performance between GPU 1 and copy to CPU. So first you do it. Okay, GPU 1 and copy to CPU. I am sending the code in your comment box. You just run it. Then we will see the utilization of the PCI Express bus interconnect. Okay, so that will give you a lot of elegant idea about how to explore the PCI Express bus. Okay, so that thing we are going to experience now. So please incorporate it. You will get the run on GPU 1 and copy timing. Okay. Once you are done with it, just let me know. Then I will show you that how to utilize the PCI Express bus. Okay. Okay. Peripheral component interconnect express bus. So here also you will observe that rather than calling wait all multiple times, npx.wait all multiple times, it will save the time. You see, once you run it, GPU 1 and copy to CPU, it will approximately take 125 seconds. If we take the summation, run on GPU 122 seconds, CPU 3 seconds, so 125 seconds. Now, if we are doing it all together, like the earlier example, when we club the GPU 1, GPU 2 together, here we are basically clubbing GPU 1 and copy to CPU together. So once clubbing them together, you can see that once you take all the npx.wait all, so your timing it is printing as 105 second. Okay. So if you see the earlier summation and this particular summation, it is quite lesser than the earlier case. Okay. So 125 second, this is 105 second. So that means you are optimizing your time. Whenever you are removing the factor, wait all factor multiple times, wait all factor multiple times, you are basically successfully paralyzing it. And you are becoming lesser dependent on the front end because you are making the system front end independent. Because at the end of the day, your computational task is being performed by the backend. Okay, and you are getting the output run on GPU 1 and copy to CPU. Here you see 105.5694 second. Okay, so this type of output you are getting. So in earlier case, already I believe that already you have run it. Once you are done, just let me know. Okay, great. So in your case, GPU 185 second and CPU copy to CPU 1.6. Great. So I can consider it as on an approximation 86, 87 around it is going. Now you check. I am copying the this part run on GPU and copy to CPU together. So just check how much time it is taking. Okay, so very nice. So everybody is getting result. So check that whatever the summation you were getting earlier case, now by reducing it with the interconnecting between, what we are doing here, basically we are putting an interconnection between copy to CPU and GPU 1 with the help of PCI interconnect bus. PCI means peripheral component interconnect express bus. So it is basically utilizing the optimization, basically what we call the system optimization. It is doing by reducing the overall time, and the way the lesser you will use npx.wait all, it will give you much more better result. Okay, because as I told you, this is the barrier in terms of the asynchronization, computation and parallelism, like we have seen earlier also. So I request all of you to kindly incorporate this thing and check the time now you are getting. So you will be able to see that it must take much lesser time than the earlier case. So let me know once you are done. Okay, excellent. Now you compare the timing. I am requesting all the respected participants, those who are completing it, kindly compare the timing. Earlier it was run GPU one and copy to CPU, add them, and now you see after doing it combiningly, you must get incorporated in much lesser time. Okay, while running on GPU one and copy to CPU together, it should take much lesser time. In my case, you can see in the first case it is approximately 125 second, and the second case it is 105 second. Okay, please go ahead. Okay, great, great, excellent. Okay, fine. So I believe now all of you are getting the idea that how to optimize your code. Okay, by running them together with GPU one and copy to CPU. Okay, rather than running them separately and using npx dot wait all multiple times. Okay, the lesser you will use, the better will be your code, and the better optimization you will get. Okay, and here the peripheral component interconnect PCI Express bus is playing a very very significant role. So in general, if you have seen that whatever we have discussed so far, that if you can see the screen, that there is a dependency between computation and communication. YI must be computed before it can be copied to the CPU. So those factors we have to keep in mind. And fortunately, the system can copy y minus I minus 1 while computing the yi to reduce the total running time. That is where the PCI Express bus is playing a very very significant role. Okay, so basically it was, sir, in your case, but in our case, local machine, how does performance varies from one person? Well, so you see, as I told you that you are using a sharing platform. Okay, so it is infrastructure as a service. Google providing Google Colab as an infrastructure as a service. You are using Google Cloud platform, and it is infrastructure as a service. So definitely, multiple people are accessing this as multiple time. So definitely, time is going to vary. But the main objective is that whenever you are using both of them together, whether it is less taking lesser time or not, that is important. In my cases it can take 103 second time. In your case it is 85 second. That is fine, no problem regarding that. But the main objective is that when you are incorporating it separately and adding the timing together, and you are incorporating them together, how much time difference you can observe. Are you being able to optimize it? That's the thing matter. Because you are using this type of Google Colab platform, always remember these are the infrastructure as a service. Google is providing us with free GPU. You are getting the GPU support also. That is the NVIDIA Tesla support you are getting basically. So make sure that whatever the outcome you are getting, that is justifying your objective or not. Okay, so once you are running it in your personalized system and somebody is running in their personalized system, then it will matter with the device specification. Okay, what are the GPU specification is there, what are the CPU specification is there, those type of comparisons then will take place. But here in Google Colab, you are using the GPU provided by the Google, GPU support provided by Google, and multiple people are accessing it, so it affects. Okay, time to time it will vary. That's the reason it is varying. But main objective is that whether you are being able to optimize your code or not. That's the thing you have to check. If you are being able to optimize it, your purpose is done. Otherwise, you have to check your loopholes in your code and you have to execute it. So in a summary, we can whatever we have discussed so far, we can tell that the modern systems have a variety of devices with multiple GPUs and CPUs. So it can be utilized in parallel manner, okay, in asynchronous manner. And if you see all the model system has a lot of resources, communication resources are there. For example, here we have used the utility of the PCI Express bus, peripheral peripheral interconnection bus, okay, and then storing it, for example, typically using the solid state drivers, okay, and trying to get the optimum efficacy. Okay, so backend can improve the performances through automatic parallel computation and communication. So that is the end of the day. This is the motto. So we have seen the hybridization, we have discussed about the asynchronization, and we have now seen the system efficacy in terms of the parallelism. Okay, so what I will do, I will share all these codes with all of you over email. So meanwhile, if you have any discussions, any queries, any question, you can ask me. So this is the end of this particular script. Okay. So let me know if you have any question or doubt, or do you want to explore any further notebook on GPU? Let me know. Now it's up to you. We have some time left. If you want, I can show another notebook, or we can stop here and you can ask any question or queries that you can do.
Participants are given unmute permission now. So you can unmute yourself and directly you can talk to the speaker if you have any query. Or else you can write in the chat box as well.
So I can see, okay, someone has written. Thank you, Ankurji. Thank you very much for your precious feedback. Okay, thank you. So one participant has said that we can go with another notebook. So ma'am, I am asking for your permission. Do you have much time to go with another
No,
notebook?
definitely we can
Okay,
continue.
okay. Then we can discuss another GPU examples with another notebook. Okay. Thank you. Okay. So we will see another notebook with some more GPU examples. How can we utilize GPUs in terms of the deep learning implementation purpose? So let me share the screen with all of you. And okay, thank you, Orpita madam, for your kind feedback. Thank you, Somadip sir, for your kind feedback. Okay, thank you. So let me share the screen with all of you. So please open up your new notebook, okay, and you can click on file button. Already all of you are now accustomed with it, how to open new notebook. and you can give the notebook name as mxnet use GPU deep learning. Okay, and the runtime, okay, runtime section, you can go there, change runtime type, you can do it, click on it and select GPU. Okay, so what I am doing, I am in the comment box section, I am just sending you one by one code, similar way like earlier you have done. You have to do pip install d2l and mxnet. Okay, I am just sharing the code in your comment box section. Please incorporate it one by one. So I have shared it in the comment box section, so kindly check it. Once you run it, like earlier cases, you will be able to see following outcome. Okay, successfully installed graph vij and mxnet cu101. Now you see the GPUs, like I was discussing that we discussed about the rapid growth of GPUs. Okay, and like I was mentioning that when the deep learning mathematical theory came up, take place, nobody has thought that practically it will be deployable, because then there was no software framework, there was no hardware support. In 2007, Theano first came up with symbolic programming based framework. Then we thought that it is possible to softwareize approach, but what about the hardware support? So thanks to Nvidia in 2012 they came up with that, and then Google with tensor processing unit platform, and now Google is also providing TensorFlow Lite for the mobile version. So edge computing related stuffs we can deploy there. Always remember that one thing, that only basing on the imperative programming we are not being able to code, I mean develop any product. Whenever you have to develop product, you have to go by the hybrid based approach, at least with symbolic approach. And your system should follow asynchrony and parallelism, such that your system can become front end independent, and at the back end you should have some strong processor, some fast executable codes like written in C++ platform. Okay, so GPU has made to execute the programs even in thousands times faster, depends upon the several system specifications and all. So basically you can utilize them, you can go by the combinations of CPU GPU, you can take the advantage of single GPU, you can go by the multiple GPU. So those types of details you can explore. So first of all, whatever the system Nvidia is installed in your machine, I mean in whatever the Nvidia support you are getting, what is the version support you are getting from Google Colab, so please check out with this version. You will be able to see, for example, in my case, it is showing 11, release 11. Currently, it is 11.3 in 2021, up to date uh, CUDA release. If you see the CUDA version released, which is quite elegant for the parallel processing purpose. Okay, so you can type this code and explore in your Google Colab, and you can check the current version facilities you are getting. Okay, you will be able to see here. Do not worry, I will share all those IPUNB file, interactive Python notebook file to all of you. I have written the texts are there to guide you. That's the reason all those texts I have incorporated there for your guidance purpose. So do not worry, it will be shared with the organizers, and they will send you. Okay, so nothing to worry about it. So once you will be able to see this CUDA details, current version of the CUDA, and now you want to check the NVIDIA SMI instructions. You can explore code. You can explore to check the graphics card information. So you just simply write it in your R console NVIDIA SMI. Okay, and you will be able to see the graphics card information on your Colab. So you just check it. So you'll be able to see the details of the NVIDIA SMI, all the details, whether your GPU is engaged or not, everything you will be able to see. As I was mentioning that we are using the NVIDIA Tesla K80 version. Okay, and you can see whether your GPU is engaged or not. In my case, you can see no running process found. If in your case any GPU is engaged, it will show that. Otherwise, it will show no running process found. Okay, so in this way, you will be able to see the whatever the activity you are doing, what are the CUDA version you can use, what are the GPU version you are using. Every details you will be able to explore there. Okay. Now we can see we will be able to explore the computing devices, for example. So how we are doing the computational stuffs, we're exploring the computational stuffs in Google Colab with the help of GPU. So basically you see that we can specify, in earlier example we have seen that we can specify the CPU or GPU, whatever we are exploring out. So for storage and calculation purpose. So in generally in MXNet, I was mentioning that CPU and GPU can be indicated with CPU function and GPU function. So the CPU function under the parenthesis will means that all the physical CPU related memories. Okay, and this means that MXNet calculation will try to utilize all the CPU cores. Okay, and however the GPU, if only represents the one card or corresponding memory, so that means if you write GPU I, so that will give you the essence of the ith number of GPUs. So if we are going with the two GPUs, then how will you write it? GPU 0, GPU 1, because always remember Python and Pythonic platforms are zero indexing. If you are writing GPU 0, that means there is one GPU. If you are writing GPU 1, that means two GPU. In case if you don't have two GPUs, then GPU 1 will redirect to CPU. Okay, your existing CPU. But CPU function, CPU with function sign implies all the necessary physical CPUs and memory. So that is the difference. But GPU, in case of GPUI, if you are writing, that means all the existing ith number of the GPUs in your system. Okay, so Python is always a zero indexing language. Okay, it starts with zero indexing. In R, in contrary with R is one indexing. Whenever you are writing index in R, you start with one, counting one. But in Python or Python related platform, it goes with 0. 0, 1, 2, 3. In this way, you keep on writing. So if you are writing this code, for example, in this manner, that from MXNet import N, NP and all those things, once you done it with D2L and all those importing, then you npx.cpu and npx.gpu. So it will give you CPU 0, GPU 0. Okay. So as it is only showing GPU 0, it is desirable that in your system it has only one GPU. So that number you can also verify. So first you incorporate this, then you can also test that how many GPUs are present in your system as well. So once you are done with that, let me know. Then you can verify the number of the GPUs with npx.num_GPUs function. Okay, and you will be able to see the available number of the GPUs for your executional operation purpose. Okay. Yes, that should appear. CPU 0 and GPU 0. That should appear. GPU 0 stands for GPU 1, one GPU. Okay. Now you can verify your number of GPUs available in the system with npx.num GPUs. Okay, that should appear. Yes, Abhishek sir, yes, Amit sir. It will come like that. npx.num GPUs. So if you once you are running it, just check it in your system, that you will be able to see the number of the GPUs present in your system. Okay, great. Somudip sir, thank you. So let's wait. This is 134. Let's wait up to 135. Then I will move to next part. Let's other to complete it. So then we can see the two convenient function allow us to run the code if requested GPUs does not exist. Yes, one GPU. Yes, that is what I am mentioning. So we'll be able to see that whether your GPU is existing or not on the basis of we are writing one code. If the GPU is existing, it will be executed by GPU. If not, it is existing, then it will go by CPU. So in this way, you have defined try GPU I0 with initiating I0, and then def try all GPUs. Okay, so it will give you all the corresponding outcome. Now your system has one GPU. So basically what will happen, it will show the GPU 0, CPU 0, and particularly GPU 0, because this will print for the try all GPUs. Try all GPUs will print GPU 0 under list, because you have only one list, because try all GPU will print the result in list. If you have more than one GPU, for example, if you have two GPUs, then it will come under the within square bracket. In Python, within square bracket, we assign list. All of you know that. So it will show GPU 0, GPU 1 for two GPU. Okay. It is here only, we have only one GPU. Within the list, it is showing GPU 0. And try GPU 0, it is existing GPU. Try GPU 10, there is no GPU 10 actually. It is just to give you the printing these CPU facilities. In order to incorporate CPU facilities, it has been given there. Because there is no try GPU 10, it will redirect to CPU. What is the code written there? That if there is not existing any GPU, then it will redirect to system to run by CPU. So whether your code is performing correctly or not, that's the reason deliberately it has been given try underscore GPU 10. Actually, there is no such GPUs existing in the system. So it will print CPU 0. Okay, it will redirect to CPU. That means your code is perfect. If in your system GPU is there, it will be executed by GPU. Otherwise, it will redirect to CPU. So that is the main motto. Okay. So your system will remain engaged. The main motto is that your system should remain engaged with optimum performances. And how can you do that? With all those tricks you are learning from here. Okay, so let me copy paste this code. You can, such that you can run it in your Google Colab. So incorporate it and let me know once you are done. Then we will see how can we relate the tensors with GPU. Okay, how can we execute certain operations with GPU. So this is 137. Please complete it by 138. Then we will move to, yes, absolutely. This type of output will come. Try underscore GPU function will give you GPU 0 because we have only existing one GPU. Try underscore GPU 10 will give you CPU 0 because there is no other GPUs. Okay, so it will redirect to CPU. And try all GPUs. It will print the list of GPU. You have only one GPU in your list. That's the reason under square bracket it is printing GPU 0. Because in Python related platform, your list will come under the square bracket. If you are writing in code in R, then it would have used the parenthesis or first bracket. But it is Pythonic platform, your list will come in square bracket, within square bracket. So now we will explore the tensors and GPUs. Okay, you always remember that, for example, by default, what is this according to setup by default, tensors are created with CPU. So if you want to check one query that where your tensor is located, the simple extension is that whatever the variable name you are creating, which you can utilize with CTX. Okay, so for example, I am defining x equals to numpy array 1 to 3. Okay, now for example, I want to check the location of it. So I will use the CTX extension. So x.ctx will give you the location. Here, for example, by default, as I said, the tensors are located into your in CPU. So it will give you the location of CPU 0, it will print. So I am just sending you it in the comment box. Please incorporate it and let me know. once you are using CTX extension with the variable name, it will give you the location where it is stored. Yes, CPU 0 will be the output, because by default tensors are always stored in CPUs. So it should give you the CPU 0 output. Thank you, Amit sir. Thank you, Abhishek sir, Somadip sir. Very good. Thank you. Now, once you are done, we will explore the storage on GPU. So I will wait up to 140, then I will show you how to do the storage on GPU. So basically, in case of what happened, that if you want to, there are several, actually, if you want to explore on GPU for the sensors, so you can do it in many ways. So one trick is that CTX, you can use the CTX argument under the try GPU, because try GPU is assigning GPU 0, whatever the existing GPU support you have. So that's the reason under the X variable, we are defining numpy arrays 2 by 3. And then what we are doing, it is an array of 1, because we are using np.1s. Then we will put the CTX argument with try GPU, because within the try GPU, the existing GPU is there. So once we are printing it, you can see 2 by 3 array of 1s will be printed, 2 rows, 3 columns, as per the definition we have given there. So along with that comma, it will CTX will indicate the location of GPU. So try GPU, existing 1 GPU, so location will be GPU 0, because Python is a zero indexing language, as I told you. So for 1 GPU, it will be GPU 0. Okay? So this is how you can incorporate it. Okay, so I believe all of you are done with it. So let's see the storage on GPU. How can you make the instance storage on GPU? It was in CPU by default, but now I am making the storage in GPU. So just simply, simply we are doing the using this CTX extension. Okay, and then you will be able to see. Now see this beauty of this code. Okay, you will be able to see that you have made the storage in your GPU 0. Okay, so now I am moving to the next part. Let us create a random tensor. Okay, on GPU. Now, one to keep in mind that our system has only one GPU. So whenever we are talking about the second GPU, that means it will read CPU, because you can't get this CPU, your system don't have the second GPU. If it was there, then it would have been executed there. But if it is not there, then your try GPU 1 code will redirect it to CPU 0. Oh, very good. That should appear. Okay, very nice, Abhishek sir. So now we are trying to explore it in second GPU, but our system don't have second GPU, so it will redirect to CPU. So this is how you can implement it in your system. So basically you run it there. I am just copy pasting the code in your comment box such that you can run it in your system. So run it and you will be able to see that 2 by 3 array, it will print 2 rows, 3 columns, and it will give you the idea that there is nothing. You can see in earlier case, whenever it is a GPU location, it is under with comma in the result section, you are getting CTX equals to GPU 0. If there was existing GPU 1, then in your result, with along with that array of code, it would have printed comma CTX equals to GPU 1. But you don't have the second GPU. That's the reason it is redirected to CPU 0, and you are getting this type of output. So whenever you are getting plain output of array without mention of CTX, remember that by default it is executing in CPU, not in GPU. The operation is being executed in CPU, not in GPU. Okay, very nice, Amit sir, very nice, Abhishek sir, Somadip sir. So we will go to the next example. Okay, thank you, Vithinil sir. So now we will see the copying operation. Okay, so how can we do that? So basically, if you want to compute x plus y, we need to decide where to perform the code. Okay, now for example, if I have made a copy x to GPU, okay, then where I will get the outcome. Okay, print x, print z. So that is another important thing we need to take care of. Okay, So basically x2 copy try GPU1. So basically what is happening there, my x is in GPU. That's the reason whenever you are printing x, it is showing you GPU0. But whenever you are copying the result with GPU1, I don't have GPU1, that means it is redirected to CPU. That means Z is being stored in CPU, but X in GPU. Okay, that's the reason whenever you are printing Z, it is giving you array of ones, but you don't have any indication of GPU. That means it is stored in CPU. Okay, so I am sharing it in the code in your comment box section. Please incorporate it. So now you are quite accustomed with that, which operation can be performed in CPU. You can incorporate same thing in GPU. Whether your variable in GPU, you can make it copy to CPU as well. So this is how you can make interactions. Definitely, print X give you GPU location 0, first GPU, because it was there. But Z, you are copying it to try GPU 1. You don't have second GPU, so it will be printed in CPU, and that's the reason you are not getting Z array of, but it is indicating any GPU. That means it is in CPU. So this is how you can trade off that which attributes or devices and when, how to use it, which, when, and where you have to use. Everything now you know. 3Ws is quite clear to you. Which, when, and where. You now know it, and you can explore it at summit level. Okay. Now, for example, you want to execute y plus z. Now, whenever you are going to making the summation operation, you have to make sure that both in CPU or GPU. Otherwise, it will be problematic. So your y is also in CPU, z is also in CPU. Your summation result will also be in CPU. It will not move to GPU until or unless you are copying it. Okay. So do it. You will get the array result without any GPU extension. That means your all operations has been done in CPU. Because y was in CPU, z was in CPU. Now, if you are doing summation, your result will be in CPU, not will be in GPU, until or unless you are copying it. Okay. Now you want to check that whether Z is in CPU or in the second GPU. If second GPU is existing, then true. Otherwise, it will redirect to CPU. It will be true, because here try GPU underscore 1 onwards, whatever you may give, it will redirect to CPU. That's the reason it will print true. So this is the way you can check the existence of your variable. Okay, whether it is in CPU or not, with as underscore in CTX. So CTX is playing the role of whether your variable or tensor or array or list is in CPU or GPU or not. That type of thing will get. So output will be true. Okay. So I have added few side notes there. So you can go through them. So last example, because already we are over, it is 147 over by time. So I'm just giving you last neural network example and the functionalities of GPU. So here neural network, we are specifying on GPU, we are executing on GPU. So what we are doing, we are defining net equals to nn dot sequential function, and then we have appended it to the dense layer, and we are initializing it in CTX equals to try GPU location. So you are basically giving you the GPU extension. Okay. So we are incorporating whole operation, neural network operation in GPU. Okay. Instead of CPU. Now what will you do? Once you have done it, okay, we were defining x equals to a new numpy array of ones to, okay, and now we are giving it ctx try underscore GPU. Now then we are printing net x, so it will give you the result. Because we are executing in GPU, so in your result extension, it will be an argument section. It will come as ctx equals to GPU 0. Okay, that means the whole operation has been performed in GPU. That is the proof. So see the beauty of this execution. Now you want to check that whether these model parameters are stored on the same GPU or not. So that check net 0 data dot CT extension, it will show the GPU. That means your all the model parameters, include weight and all, are being stored in GPU. Okay. So Amit sir, Abhishek sir, all of you have got the correct result. So let us check the location of weight, all the model parameter, whether the model parameters are in GPU or not. They should be in GPU, like I was saying, whenever you are executing the operation. Thank you, Somadip sir, you have done correctly. So whole execution, it is addition, subtraction, model parameter execution, whatever you are doing, that should be in the same devices, whether in CPU and GPU. You are adding Y and Z. You want to get the result. Y, Z result. Either everything will be in CPU or in GPU. Can be hybridization of that. You can copy and do the parallel execution. That's a separate thing. But for example, here you are executing the neural network operation. Okay. Every operation is done on GPU, including the model parameters are also existing in GPU. Okay, you can try this comment. Net zero with data, whatever parameters you see with the CTS extension, it will give you GPU zero. That means whole operation is being executed in GPU. And if the GPU is not existing, you have to code in such a way that it should redirect this CPU. Okay, so in a summary, you can say that we can specify devices. Okay, we can specify devices for the storage and calculation either in GPU, CPU, or in combination of both. So deep learning frameworks require all the input data. It should make busy all the threads. Okay, whether it is CPU threads or GPU threads, it should execute and keep it busy. Okay, so that's the reason we have to be very, very careful. Okay, about the parallelization, asynchronization, and hybridization. And along with that, the more the bigger will be data, the more the bigger will be computations. The GPU support is going to play a very, very significant role. Okay, okay, Somadip sir, you got the correct answer. Okay, so that's all for today's session. I hope that with subsequent these two sessions, all of you got some insight about how to tweak with the codes and how to treat the codes with time complexity, processor, CPU or GPU, or even the backend coding platforms. Okay, like C++ to make the code faster. Okay, these type of tricks I hope you now have learned. Whenever you are going for the this type of high level research, or for example the coding, I mean development of product, this will play a very, very strong indication role in your mind that where to use which one. Okay, three W's: where, which, and how. Okay, so this is how you can incorporate it in elegant way. So I believe this session is quite useful for all of you. Kindly share with us your feedback in comment box. Okay, and I have my contact details with all, I mean you have my contact details. Okay, so feel free to contact me for any doubt, and I will definitely email this four collab sheets, Python notebook, interactive Python notebooks, to the organizers. And finally, I am quite thankful to all the organizers, IEM team. It's an institute which is creating historical impact on the eastern region for last more than 25 years, and we all are proud to be associated with IEM directly or indirectly, in which means whatever means is possible. And I am thankful to giving me two subsequent session, conducting two subsequent sessions, such that I can share this type of extensive coding to my respected participants. Because with 1 hour talk, it was not always possible to give the coding demos and discuss in so vast manner. So I am thankful to all of you again, and thanks to all the participants for your kind collaborations, because you see, doing things remotely is not easy task. So it is all your passion which made the session successful. Okay, thank you very much. Thank you all. Thanks a lot.
Thank you, sir. This was an excellent session and it was very interactive too. We would definitely like to have more such hands-on session in future. And
Thank you.
as sir has already addressed all the questions written in the chat box, still if you have any further query, you can directly talk to the speaker now. All of you have been given unmute permission. Participants are requested to unmute themselves and ask directly to the speaker if they have any query. All right. I hope all of you have given your attendance by this time. You will be able to see your attendance in the portal soon. Please don't forget to give your feedback in the portal after the valedictory session at 3:45 p.m. Also, please remember that the test will begin today at 2:30 p.m. sharp. All the participants are requested to find the test link in the WhatsApp group. It will be a 100 marks test and an MCQ test, and the qualifying marks is 60%. So if you have any query, you can talk to the speaker now. All right, I don't think that there is any further query from participant side. Thank you very much, sir, for delivering such a wonderful talk today. We all have enjoyed a lot. And thank you all the
Thank
participants
you.
for your time and patience, and wish you all the best for your examination today. Hope to see you again in the valedictory session at 3:45 p.m. Thank you very much. Thank you, Shobhosachi Mukhopadhyay, sir. Now, we would like to present you with a
Kindly email
small
me
token
this
of
certificate. It looks very nice. It is looking
this
very
is
nice. Very
prepared by
nice.
one of our
Thank you.
team member,
Kindly email
Tufan
me that.
Shah. Yes, definitely we will email
Oh,
this
great.
to you.
Great. Great.
So this
Excellent.
is,
Excellent.
please accept just a small token of appreciation from our side. Thank you very much. So we are close. The session will be on. If the participants want to stay here, they can. Otherwise, we can again join the session at valedictory at 3:45 today. Thank you very much.